Hello everyone. In the previous lecture, we discussed about fluid statics, in which we had taken an element. Uh, the length in x direction is given by delta x, and in y direction it was given by delta y. And on this element, we applied the force balance. Force is given by surface force plus body force. The surface force was given by the pressure force at the left surface and the pressure force at right surface. Pressure force at right surface, which is at a small distance from the left surface, is given by the Taylor expansion, that is P plus del P by del x into delta x. The body force is given by body force per unit mass into mass is equal to mass into acceleration is given by rho into delta x into delta y into 1, that is mass into acceleration in x direction. This gives the three equation: minus del p by del x plus rho bx is equal to rho x. This is in x direction, and similarly in y and z direction. So we used this differential equation in order to derive the formula for pressure at any point. If I know the pressure at one given point, with respect to that, how can I find the pressure that is given by P2 is equal to P1 minus rho g into Z2 minus Z1. Z2 minus Z1 is the difference in height. The problem that we discussed in the last class was a semicircular gate, which is at the bottom of a wall. What is the total amount of torque which is linked with that particular gate which is at the bottom of the wall? So in this variable problem, we took an element and we evaluated what is the total amount of torque acting at that element, and we integrated it for theta and r in order to evaluate the total amount of torque which is acting on the element. This was the problem we discussed. Then we discussed force on curved surface. If I have any curved surface, it is placed in a liquid, then how to evaluate the force on the curved surface? The method we described, that if I have curved surface of AD, we will extend a surface from A all the way up to the interface of air and water, and from D also in the same way we will extend a hypothetical surface from D to the surface of or interface of air and water. And we found we applied the force balance in x direction and force balance in y direction in order to obtain what is the total amount of force acting on the curved surface. The horizontal force acting on the curved surface is given by Fh1 minus Fh2, where Fh1 is the force exerted on the surface AB extended perpendicular to the seat on which I am writing, and on CD the force exerted is Fh2. So pressure at the point which is at the center of A and B, and multiplying that with the total area of AB, which is a surface which is extending perpendicular to the sheet of paper. And in the similar fashion, Fh2 is given by pressure at a point which is given by the center of C and D, and area of the element CD, which is extending perpendicular to the sheet of paper. So in that way I can find what is the force in the horizontal direction. For the force in vertical direction, we can say then force in vertical direction is given by weight of the liquid. Okay, this was the thing that we discussed in the last class. Now in this class I would take some examples of how the force is acting on the curved surfaces. We want to find that with the help of some example, and then we will use the same result that we discussed in the last class. Okay, so let us take a problem. The first problem is this is a cylinder which is extending perpendicular to the sheet of paper, and it can be seen by a circle only, and I will divide it into 4 parts, and this is liquid is filled here. This is the surface, and from here liquid is filled like this. This is A, B, C and D. AD is the part which is exposed directly to the atmosphere. Now we have to find what is the total amount of force acting on the curved surface A, B, C, D. Where AD is exposed to atmosphere, it is not exposed to the liquid. This is the liquid part. All these thing is liquid part. Okay, this is liquid. Now I have to evaluate what is the total amount of force which is exerted on the surface ABCD. Okay. So what we need to do, from the curved surface I can draw a line extending all the way up to the surface. Okay. And D is exposed directly to the surface. CD is the curved surface, so it is directly coming to the surface, to the interface you can say. So we cannot draw any line here. We can draw only line from the B all the way up to the interface of water and air you can say. Now what is the force acting on the fluid on the curved surface BC? What is the force exerted? I will draw it in black. I will set the portion in the black. Whatever force exerted on CD by the fluid is weight of this particular liquid. Note that it is solids, but still what is the force acting is, if this much amount of volume is filled with liquid, what would be the force acting? Okay, so this much is. Now what is the amount of force which is acting on AB? For AB, if I am extending the from B to the interface, this will be the portion that I will get. Now the portion that is coming in both force acting on BC is in upward direction. Force acting on BC is in upward direction, and force acting on AB will be in the downward direction. And the part which is common will get cancelled out. This red and the black part that I have drawn will get cancelled out, and the total amount of force which will be acting on AB plus BC, or AC, AB plus BC comes out to be AC, is given by weight of, let us say this point is O, weight of liquid in AOBC minus weight of liquid in AOB. Now what I can say, if I subtract this, I will get weight of liquid in ABC. This is given by pi r square by 2. This is the area of the circle into L. This will give the volume of the cylinder. If I consider only ABC part, this will give the volume. And what is the density of fluid? Rho F into volume into density mg. So this will give the force. Okay, so pi r square by 2 into L into density of the fluid into g. This is the force which is acting in the upward direction on ABC, on surface ABC. This is F1. But we have to find what is the force acting on CD as well. So force acting, suppose F2 is the force which is acting on CD. Force acting on CD is equal to weight of the liquid given in red color. This is because D itself is going onto the surface. Here what was the case? B was not onto the surface, so we had to extend a line from B to O. But here in this case, D goes all the way up to the surface, so I cannot draw any line from D which goes onto surface. D itself is on the surface, so I do not require to draw any line from this edge. Okay, and whatever volume is occupied for, we will find if density rho F fluid is filled in that volume, what would be the total weight, and that equivalent to that weight, the force will be applied on that curved surface. So what is the total amount of weight which is kept in CD? That is given by pi r square by 4 into L. This will give me total volume into density rho F into G. So what is the total force F acting on the surface ABCD? That is given by F1 plus F2. Note that the force applied on CD will also be in the upward direction. So what I can say? Pi r square by 2 into L into rho f into g plus pi r square by 4 into L into rho f into g, which can be given by total force F is equal to 3 pi by 4. I can 3 pi r square by 4 into L into rho f into g. This is the total amount of force which is acting on ABCD in the upward direction. Okay. What is the horizontal force? This is Fv. Horizontal force Fh is equal to Fh1 minus Fh2. This is given by B is at a height at a depth which is located at R from the top or R from the interface, or I can say R from O, because this is R. So what is the total pressure at point B, because it is at the center? What is the total pressure? That is given by rho f into G into H is given by R. And what is the total area associated with the left surface? That is given by length into 2R minus, for this force, equivalent force is acting on R by 2. This total length is given by R. Let me change the this total is given by R, and the force at which the location at which force is acting is given by R by 2. So what is the total amount of force? That is given by rho f into G into R by 2 into length will be same into R. Length into R will give the area, and rho f into G into R by 2 will give the pressure. If we find the difference, that will come out to be rho f into G into LR square minus, that will come common, rho f into G into L into R square, 2 minus 1 by 2. That comes out to be 3 by 2. By 2 rho f into G into LR square. Okay, so in this way, on any curved surface, I can find what is the force acting in the horizontal direction and what is the total force acting in the vertical direction. Okay, the derivation we did in the previous class, and drawing from that derivation, we have solved this problem. Now coming on to one more problem. This is a variable problem. Okay, this is the variable problem. In this problem, I have this y-axis, I have this x-axis, and how y is varying as a function of x is given by this. X is equal to ay cube. This is y, this is x, and up to this height d, liquid is filled. Now I have to find what is the total amount of force acting on the surface which I have drawn, which equation of which is given by x is equal to ay cube. Note that this surface is extended perpendicular to the sheet of paper on which I am writing. I have just shown the two-dimensional figure because I can draw just two-dimensional figure on the sheet of paper. So let us try to solve this problem. So in order to solve this problem, I have to take an element at a distance y from the top. Let us say at a distance y from the top, I have a differential element of length dl. Because dl is, I have to take dl because it is not varying just in x direction or just in y direction, it is varying in both. So I have to take dl. I cannot take dx or dy, but I have to take dl. Now in solution, what I can say, that this is the almost it, because the length of the dl is very small, I can assume that the surface which seems curved can be taken linear because the length of dl is very small. Now this is given by, for this small element, this is given by dy, and the dx, this is given by dx, this is given by dl. Let us say at this point this angle is given by theta. Now what I want to say is force is also acting in this direction. Okay, so force is acting in this direction and it is normal to dl. Okay, now let me write dl little bit here. If I extend on this surface, this is the direction of force. This is the force acting at the element dl in the perpendicular direction, and the component of force in vertical direction is given by Fy, and the component of force in the horizontal direction is given by Fx. This is Fx. Okay, so this is a small area, so the force is given by the differential of the force in x and y direction. Now what is the dfx? Dfx is given by the height from the interface between air and water is given by y. So rho into g into y, this is the pressure at this point, into dl into 1. Suppose 1 is the length extended perpendicular to the sheet of paper. So this will give the total amount of force, and the component of this force in x direction is given by this figure. Let us look into this figure. If this suppose I mark this as a b c, the angle given by ACB is given by theta. So what is this angle? This angle will also be theta by alternate angle. This angle will become 90 minus theta, and this angle will become theta. So what is the component of force in x direction? Cos of 90 minus theta or sin theta. So what is the force in y direction? dfy is given by same element is given at a depth of y. So the pressure at the point y is given by rho into g into y into dl into 1. This is the total amount of force, and its component in the y direction is given by cos theta. Now I can say that dl into from triangle ABC, I can say cos theta is equal to dx divided by dl, and sin theta is given by dy divided by dl. Dx is equal to dl cos theta, and dy is equal to dl sin theta. So putting these values of dx and dy, or dl cos theta and dl sin theta, in the two expressions of forces, I can write dfx is given by rho into g into y into dl sin theta is given by dy, and the force in y direction is given by rho into g into y, dl cos theta is given by dx. Okay, now it is very simple problem. This height is given by if this is y axis, so this value is given by y. So the depth from the interface is not given by y but by d minus y. So I have to replace this as y by d minus y. Let me write it, rho into g into d minus y, because y is measured from because my coordinate axis starts from the origin, so y is measured from O. So as I move up, it will give y, but at what depth it is located from the interface is given by d minus y, and we are concerned with the depth at which it is located from the interface of water and the air. Rho into g into d minus y into dl cos theta, rho into g into y dx, and here also I have to replace rho into g into d minus y, dl sin theta is given by dy, and rho into g into d minus y, and dl cos theta is given by dx. This is the expression. Now I can integrate the two equations in order to obtain what is the total amount of force acting in direction x and at direction y throughout the entire point from O to, let us say, this point is S. So for force on OS in x direction is given by integral of dfx, that is given by integral of rho into g into d minus y into dy. Now variable is y, so y can be integrated from 0 to d. So rho into g into d into integral of dy is given by y from 0 to d minus rho into g into y square by 2, and the integral is given by 0 to d. Rho into g into d square minus rho into g into d square by 2. So I can say this is equal to rho into g into d square by 2. Okay, this is the force acting in the x direction. Now I have to find what is the force acting in the y direction. So I can write integral of force. At 0 the force in x direction should be 0, and here it is fx. dfy 0 to fy is given by 0 to d rho into g into d minus y into dx. This is the formula. Now the variable is y and x both are varying. So what I can say, we have got the equation which represents x is equal to ay cube. X is equal to ay cube. I can find dx. Dx is equal to a into 3y square dy. I can put this particular thing in the expression of dfx. The integral of force in y direction is given by fy is equal to 0 to d rho into g into d minus y into a into 3y square dy. I can take the constants out. Rho into g into a, with 3 also I can now take out. Rho into g into a into 3 integral of 0 to d dy square minus y cube divided into dy. Now integrate this. 3 rho g a d into y cube by 3, that is given by y cube by 3, and putting the limit from 0 to d will give me I have just integrated and put down the limits. Okay, 3 into rho into g into a d power 4 bracket में 1 by 3 minus 1 by 4. Multiplying 3, I can say rho into g into a into d to the power 4 into 1 minus 3 by 4, that is given by 1 by 4. Rho into g into a d to the power 4 by 4. That is what we obtain. Okay. Now the force in x direction specifically I know, and force in y direction also I know. Force x is equal to something that I know, expression I don't know, that is given by rho into g into d square by 2, and force in y direction is also given by rho into g into a into d power 4 by 4. Now what I can do, the force in total force F is given by the magnitude of Fx and Fy. So magnitude is given by Fx square plus Fy square. So whatever force that we get, we can get it from here. Okay. Now the same problem that we have done using the integral approach, or by taking the small element and then integrating that particular equation of dfx and dfy to obtain what is the total amount of force acting on the surface in x direction and in y direction, the approach that we have used, or the formula that we have derived, can also be applied in this case. So let me carry the same picture that I have drawn here, and I will show you how without integration also I can obtain the same result. Okay, so I have said you that you have to extend the surface all the way to the surface. You have to extend the edge of the curved surface all the way up to the liquid and air interface. So suppose from point O I have extended a line something like this. So what is the force acting on the surface OS is given by total amount of weight which is contained in this particular volume. Okay, so the force in x direction is given by, how I can say the force is in x direction? Force in x direction is given by rho into g into, if the height is given by d, so the pressure that we have to evaluate will be at point d by 2. So what is the pressure at point d by 2 is given by rho into g into d by 2. This is the total amount of pressure. What is the total force? The force is this, since this entire height is given by d and it extended perpendicular to the seat, and the length perpendicular to the seat is given by 1, so I have to multiply it by d into 1. This will give me area. This is the total force which is acting in the x direction. Okay, so it will come out to be rho into g into d square by 2. This is what I think we have obtained. This is the expression that we have obtained for the force applied by using the differential approach, and it is exactly matching with the same formula that we have derived. Now, in order to evaluate what is the force acting on the surface OS in y direction, force in y direction, it is given by the total weight of the liquid, which I have shown, or which I have colored by using the red. So what is the total force in the y direction? What is the total weight of the liquid in, let us say this point is A, so OAS. So I can say AY cube into dy, this is the volume, into rho into g, this is the total mass which is at any point if this is dy, so what is the total amount of weight of the liquid contained in this particular element is given by A into y cube into dy. This is the total volume into rho into g, that will give the total weight. So integrating this is dfy. Integrating this, we can get fy is equal to integral of A rho g into y cube into dy from 0 to capital D, because it is varying from y is equal to 0 to y is equal to capital D. So what I can say, fy is equal to rho into A into g into y to the power 4 divided by 4 from 0 to D. This is given by rho into A into g into d to the power 4 divided by 4. This is what we have obtained by using the differential approach also. This is force in y direction. That is also given by rho into g into d to the power 4 by 4. So the same concept that we have derived, the same concept can be used wherever applied, because I have derived the concept of a curd plate is kept in a stationary liquid or a quiescent liquid. In that case, what is the total amount of force acting on that curved surface in x direction and y direction can be found by extending the first stage and the second stage all the way up to the interface between air and water. And what is the total amount of weight that is contained in that particular volume is given by the force in y direction, and whatever be the force in x direction is given by the difference of the forces from on the drawn surface from the edge of the curved surface all the way up to the interface between air and water. What is the force acting on the left face and what is the force acting on the right face? The difference of these two forces will give me the force acting on the curved surface in horizontal direction. So using that concept, you can revise the previous class. Using that concept, I can find what is the total force acting on the surface OS, and we will get the same result that we have obtained from the differential approach, which we have discussed over here. This is the problem which we have solved by using the differential approach, as well as the formula that we have derived, or the method that we have seen in the last class. Okay, now I will come on to the next topic, that is given by stability of the submerged or floating body. Submerged and floating body. So suppose I have a volume, certain volume, and suppose the body, this is the axis, let us say this is the axis. The buoyant force is acting over here and the force of gravity is acting over here. this is point G, weight is acting in this direction, and from point B, force FB is acting in the upward direction. Now if we want to tilt this, okay, if we want to tilt this, so if I want to measure what is the total amount of torque acting about a point O, the force which is acting, this W will be acting now in vertically downward direction, in this direction, and the buoyant force will be acting in the upward direction. So then let me change the direction. The buoyant force will act in the upward direction and the gravity will act on the downward direction. The point of action of the gravity is given by the point G, and what is the total force acting, this is given by W, and what is the buoyant force acting, this is given by Fp. Now what will happen about point O, if you will measure that this weight is trying to rotate the body in this direction, but the buoyant force will try to rotate the body in this direction. So both the forces, the torque which is acting by both the forces about a axis is in opposite direction. They will try to cancel each other. In that case, the body will try to stabilize. After we will give some tilt, the buoyant force will try to take the body back into its position by because the action of the force is in that direction, and the force weight will try to rotate the body in the other direction, but that will be countered by the buoyant force. And you can see the torque which is acted by the buoyant force is even greater, because buoyant force is acting at this lever arm, and this is for buoyant force, and for gravity it is given by this lever arm, gravity for this lever arm. So the lever arm which is greater for the buoyant force gives the more magnitude to the torque by the buoyant force. Then the buoyant force will try to stabilize the body back into its position, but the weight is trying to destabilize the body. Okay, so whichever torque is greater will determine whether the body will come to its original position or the body will not come to its original position, and it will tilt. So this is given by the magnitude of the two torques. What is the torque given by the buoyant force compared to what is the torque given by the body force. Okay, but it is for sure that if the buoyant force is acting in upward direction and the B is below the point G, in that case both the forces will try to rotate the body in one single direction, and then the body will not get stabilized. So I will write the rule for the stability of the submerged or the floating body. You can draw this figure again and write and try to draw this figure again and put G above B, and then mark the direction of the forces, and then try to evaluate what is the direction of the torques given by the two forces about the point O. In that case you will realize that both the forces are supporting each other, or both the forces will try to rotate the body in one direction, and even a small amount of deviation from the straight body, it will try to tilt the body in one particular direction, and the body will not be able to uh, it will not be able to come to its original state. Okay, so now I will write what is the rule for this. If B is center of buoyancy, at which the buoyant force is acting is above G, which is center of gravity, then stable equilibrium, if center of buoyancy is below G, that is center of gravity, then both the forces, the couple generated by both the forces will try to rotate the body in one direction, and the body will not be able to regain its shape in the original state, and we can say that even a small perturbation will drive the body to its unstable equilibrium. Okay, so then we will get unstable equilibrium. And if B, that is center of gravity, center of buoyancy, is exactly at G, that is center of gravity, then neutral equilibrium. There will be no any effect of rotation about the axis, and if I tilt the body, it will remain at that position without going back and forth, or without getting into original position, or without getting tilted in other direction. Okay, it will remain at the location at which we can leave. Okay, now the next topic that I want to discuss is fluid under rigid body motion. Fluid and rigid body motion. Suppose I have this body and I have the fluid which is kept in this body, and I want to move this particular body with some acceleration, and this is something shape of the meniscus, shape of the surface that I am getting. Suppose the angle is given by theta. The shape of the surface is given by this red line, and initially the surface was given by this blue line, and this length is given by B. Suppose I want to roll this body, and height of the liquid is given by HD. This height is given by HD. Now I have to evaluate what is the equation of the surface if I am accelerating this body with the acceleration A. Suppose the acceleration in the x direction is given by ax, and now I want to understand how the surface of the body is oriented, surface of the liquid in this body is oriented. Okay, so I will use the equation that we have derived, minus del p by del x plus rho bx is equal to rho x. This is the equation for x direction, and there is no body force which is acting in the x direction, but there is acceleration in x direction. So minus del p by del x is equal to rho into ax. This is first equation. For the second equation, I can write del p by del y plus rho by is equal to rho into ay. Now what is the force which is acting in y direction? There is no any acceleration in y direction. What is the force acting in y direction? Minus del p by del y plus rho into body force per unit mass is given by minus g. This is equal to 0. Now for interface, I can write pressure is equal to constant, because pressure is equal to atmospheric pressure. Pressure is equal to constant for surface. Everywhere pressure is equal to constant. Okay, so or equal to PAT, or equal to PAT. dP is equal to 0, because it is constant, its dP is equal to 0. So dP can be given by del p by del x into dx. Change in pressure is equal to 0. So rate of change of pressure with respect to x plus rate of change of pressure with respect to y into dy is equal to 0. Del p by del x we have obtained as equal to minus rho into ax, plus del p by del y we have obtained is equal to minus rho g dx. So rho gets cancelled, minus gets cancelled. Ax dx plus rho g dy is equal to 0. dy by dx is equal to, sorry, rho gets cancelled. dy by dx is equal to minus ax by g. And acceleration due to this, the acceleration is given by, due to the motion in x direction, the acceleration is given by ax, and the force per unit mass is given by g, which is acceleration due to gravity. So dy by dx dimension is null, and in the right hand side the dimension of ax is equal to meters square per second, and the dimension of g is also equal to meters square per second, and dy by dx is given by tan theta. At any point tan theta is given by dy by dx is equal to minus ax by g. So this is the equation that we obtain for the shape, or what is the angle which is made by the surface, which was initially inclined along x-axis, but due to the motion or acceleration in x direction, it is tilted at some angle theta. How can I measure the angle theta? Just by taking the ratio of the acceleration in x direction and divided by g. Okay, this is the first thing that I wanted to discuss. Now in the second case, suppose the body is running on the inclined surface. Suppose this is the body, and this is the surface, and it is running. This is, let us say this is direction x and this is direction y. Now I have to solve this. What is the equation of the surface of the liquid that we are taking into account? Okay, again I will do the same process. For the surface I can write pressure is equal to constant, because pressure is equal to atmospheric pressure. So the change in pressure is equal to 0. Del p by del x dx plus del p by del y into dy is equal to 0, and del p by del x minus del p by del x plus rho bx is equal to rho ax. Acceleration is in x direction is given by, since I have inclined surface, so acceleration in x direction is given by a. So in x direction I am saying that acceleration is a, and the force in x direction is also given by, because force in this direction is given by rho into, or mg. So force per unit area is given by, force per unit mass is given by rho into g. Sorry, the force which is force per unit mass is given, is multiplied, like I have to write the equation. Bx is here, bx is force per unit mass, force per unit mass. So force per unit mass is given by g. Now the g is acting in the downward direction, and this is the angle theta. So what is the force acting in this direction? That is given by rho g into sine alpha, sine theta, g into sine theta. So it is given by minus del p by del x plus rho into g sine theta is equal to rho into a. This is first equation. Similarly, I can write minus del p by del y plus rho into by is equal to rho into ay. Acceleration in y direction is given by 0, so this is 0, minus del p by del y plus rho into body force in y direction, body force in direction y. So body force in direction y is given by g sine theta in downward direction, so in upward direction it is given by minus g sine theta, rho into minus g sine theta is equal to 0. So dy by dx is equal to minus del p by del x divided by del p by del y. Del p by del x is given by rho into g sine theta minus rho into a divided by del p by del y is given by minus rho into g into sine theta. Sorry, cos theta. This is given by cos theta. This is cos theta. Okay, so this is the x. Now I can cancel rho. A minus g sine theta divided by g cos theta. This is the equation of the surface. In order to find the equation of the surface, one thing I have to keep it in mind, that at the surface everywhere the pressure is given by the atmospheric pressure. So if atmospheric pressure is constant over the entire surface, we can say that the change in pressure is equal to 0, and it is not varying as a function of x or as a function of y. So the first condition that I exploit is pressure is equal to constant. This is the first condition for the surface. So dp is equal to 0, and dp is equal to 0 is governed by the two variables x and y. So del p by del x into dx plus del p by del y into dy is equal to 0. This is something which can be exploited anywhere for surface. Now in order to find del p by del x, we can use the derived equation that we have derived for a small element and applied a force balance on this. That particular equation we can use here in order to find what is the value of del p by del x in terms of acceleration due to gravity. And similarly, the expression in y direction can also be exploited. From these three equations, we can obtain what is the shape of the surface. Okay, and for today, the last problem that I'm going to take is what is the equation of the surface if body is rotated by some angular velocity omega. Suppose I have a body which is filled up to this point by water, and it is the axis about which it is rotating, and this is something angular velocity omega, and this is the open to atmosphere, and it is given for surface. This triangle is given for the surface. This is z direction and this is r direction. Now I have to use the same concept, minus del p by del r for surface. In r or in z, the pressure is not varying, so minus del p by del r plus rho b r is equal to rho into acceleration in r minus del p by del r. Body force in r direction is given by 0. The acceleration in r direction is given by minus omega square r, centripetal acceleration. Whenever a body is moving in a circle of radius r and angular speed omega, the centripetal acceleration towards the center of or towards the axis through which it is rotating is given by omega square r. So the r is taken as positive in outward direction, so omega square r, which is in the inward direction towards the axis, so we have to take minus sign, minus omega square r. So minus del p by del r is equal to minus rho omega square r. This is the first equation. Okay, the second equation can be given by minus rho del p by del z plus rho into bz is equal to rho into az. Acceleration in z direction is given by body force in z direction is equal to body force per unit mass is given by g. G is in downward direction. If g is in downward direction and we are taking in the upward direction as positive, so what I can write, minus del p by del z plus rho into bz is minus g. This is equal to acceleration in z direction is given by 0 because there is no any acceleration in z direction. This is equal to 0. Minus del p by del z is equal to rho into g. Note that g is positive in negative z direction. The g is in the downward direction and z is in the upward direction. So that is why I have taken g to be minus g. This is acceleration in body force per unit mass bz to be minus g. Now I can exploit the condition of surface, that is given by dp is equal to 0, or del p by del x into dx plus del p by del y into dy is equal to 0. Sorry, for here we have to take r and z. The two variables are r and z here. Now del p by del r is given by rho into omega square r plus del p by del z is given by minus rho g into dg is equal to 0. What I can write? dz by dr is equal to omega square r divided by g. This gives the expression of what is the slope at any point, because here r is changing, so dz by dr at any point the slope is changing. At a different r we will have different slope, and in order to evaluate what is the particular z at a given r, I have to integrate this equation. How can I integrate? dz is equal to omega square r divided by g into dr. So integral of this is given by integral of this. So z is equal to omega square r square by g 2g plus constant. Let z is equal to 0 at r is equal to 0. At r is equal to 0, suppose z is equal to 0. So let us say this is equal to 0. Now what I can say? 0 is equal to 0 plus c is equal to 0. This implies that z is equal to omega square r square divided by 2g. So at any radius r from this axis, at this point, equation is given by z is equal to omega square r square divided by 2g. At r is equal to 0, what is z? It is equal to 0. At r is equal to, let's say r1, what is the z? Z is equal to omega square r square divided by 2g. At z is equal to, this is z1, z2 is equal to omega square r2 square by 2g. This is, let us say r2, this is r3, r4. At any r I can find what is the height with respect to point O. Let us say, if I want to say, let z is equal to z0 at r is equal to 0. In that case, z0 is equal to c. So z is equal to omega square r square divided by 2g plus z0. So in that case, what will happen? Let us say this is point 0. So in that case, this will point z0. And above z0, we are evaluating what is the height of the surface. And similarly, in this case, I can get z1 is equal to z0 plus omega square r1 square by 2g. Again, I can get z2 is equal to z0 plus omega square r2 square by 2g. Now this time, we are measuring the height from this point O, this point O. Earlier, we were using the coordinate system which was oriented here at O prime. Now we are using from O. This is something which you need to keep in mind. Any expression of the two you can use based on the coordinate axis where you are fixing. On the basis of that, you will get the expression of z. Okay. So these were few things that we wanted to discuss in this lecture. After the derivation of the force applied on the curved surface, we did some problems related to that, and we wanted to find the differential approach, go through the differential approach and find the solution of a problem. And in one problem, we just did it by using the differential approach and then showed that whatever concepts that we have discussed in the last class, that also verifies the same result. Okay. Then after that, we found how the surface, what is the equation of the surface if a body is accelerating in x direction, or if it is rotating with angular velocity omega. In that case, what is the equation of the surface that we have obtained. From the next class, this is the total completion of fluid statics. From the next class, we will use fluid kinematics. We will start fluid kinematics, and in that class we will discuss Eulerian approach, Lagrangian approach, and then we will continue further. So thank you for this class.